mute your mics unless there's something you want to say for posterity. But please unmute your mics and ask if there's anything you don't understand. Okay, right. So just want to check that you can all see the page I'm referring to over here. Let me just fix the focus. Wow, that actually made it worse. Let's try again. There we go. That's a bit better. Okay, so what we're talking about today is we're mostly going to be talking about probability density functions. But before we can get to the probability density functions, we just quickly have to finish our discussion from last week, which is the hypergeometric probability mass functions. So last week, we kind of finished off with binomial distribution or the binomial mass function. And I said to you guys that whether we call it a distribution or whether we call it a function, it's pretty much the same thing. It's not much of a difference. The only reason we now refer to it as a function is because it has that whole idea of an input-output. So the input is the number of successful events I want, and the output is the probability of getting that number of successful events. So we have spoken about the binomial one, which is revision of the grade 11 content. And I just want to quickly talk about this hypergeometric one, which is also revision of the grade 11 content. So this formula appears on your formula sheet or on your information booklet, whatever they want to call it. And what this pretty much says is the following. It says this. With a binomial distribution or a binomial probability function, what you're doing is you're saying that the probabilities don't change. So from one event to the next event to the next event, there's no change in the probabilities because the events are independent from each other. Like that example that I used last week about looking at the houses in the area that have electric fences. If the first house has an electric fence, that has no bearing on whether the next one has an electric fence or the next one has an electric fence or the next one. And because there are so many houses, it's not like I pick a house and then I have to recalculate the probabilities because now I know whether that house has an electric fence or it doesn't. You can almost imagine it's not really an infinite number of houses, but the houses are so numerous, or there are so many houses, that whether the first one has a fence or not has no influence on the probability whether the next one has a fence or not. But with a hypergeometric probability mass distribution or probability mass function, we have this situation right there. Now, this situation pretty much talks about this. It says, I have a finite population, and I call that capital letter N. So a good example of this, for instance, is I walk past a vase of flowers or a vase of flowers. Vase of flowers, vase of flowers, a pot full of flowers. There's lots of flowers. But I know for a fact that in this pot full of flowers, I have a total of 50 flowers. So N says there's a total of 50. Now what I then do, and this is what this little thing is about, I now take a sample out of this finite population. So I take a sample out of the 50. So I go and I say, I'm now going to grab out of that finite population, I'm going to grab like a sample of 10, for instance. And then what I know is I know the following. This population, that big population, is split up into two categories. So we're still dealing with a yes and a no. So what could potentially be happening here is this pot full of flowers have white flowers and then red flowers. Okay, or it doesn't have to be white flowers, red flowers. It could be something like it has yellow flowers and it has not yellow flowers. Okay, so I will divide it into two things. I will say yellow flower is my success, so not a yellow flower is my failure. So the not a yellow flower, there might be red and pink and purple flowers, but I just call it not yellow because I need those two categories. So what happens over here is that total of 50 is split up into the total number that has the property and that which does not have the property. So here I will say that 50, for instance, there are 10 yellow ones in that in the pot of 50, which means there are 40 not yellow ones. So this will be P. That is the number of elements in the total population that has this property that I'm looking for, which means obviously 50 minus 10 is then 40, which is the total that does not have that property. So that's going to be N minus P. And then I now go and I say to myself, but I'm now picking a sample of 10. So when I pick that sample of 10, I will now be able to say, what's the probability of getting one yellow flower? So R will be 1. What's the probability of getting 4 yellow flowers? Then R will be 4. Because remember, that small letter R, that is my random variable. That's my input. That's what I want to find out. What's the probability of getting 4 yellow flowers, for instance? So that means I will then say I need to get 4 out of the 10 yellow ones, which means I will then need to get 6 out of the 40 not yellow ones. So this is what I'm talking about. I'm picking 10 flowers out of 50, but the 50 is split into 10 that are yellow and 40 that are not yellow. Then I identify what I want. So my input, my random variable. And I say I want to pick 4 yellow ones out of the 10, which means I want to pick 6, because remember that one plus that one then gives me the 10. I want to pick 6 out of the 40 not yellow ones. So that's pretty much how I set this up. Okay, so that's the idea here. And the reason this is not binomial is, logically speaking, because my population is finite. In other words, because my population only has 50 items, it means if I pick something and it's not yellow, and this is without replacement, so I don't put it back. If I pick a flower and it's not yellow, then I put it down, and that means the probabilities have now changed. So it's almost like that example you did in grade 10 or grade 11 core maths probability, where you had, like, for instance, a bag full of marbles. And you said there are 4 black marbles and then maybe 10 green marbles. And I pick a black one first and I put it down. And because I put it down, the probabilities inside the bag have now changed. So I have to recalculate the probabilities. That, by the way, is a hypergeometric probability mass function. You can also do it with a tree diagram, but this formula says you don't actually have to use the tree diagram. You can just use this. This will calculate everything for you. Okay. Is there any questions about this? Are you guys at least with me so far with what I'm discussing? Okay, silence is golden. I assume you guys understand what's going on. So let's look at this example from the grade 11 textbook. It says, a team of 4 is chosen from 7 girls and 6 boys. So I'm choosing 4, which is that small letter N, from a team of 4 from 7 girls and 6 boys. So that's 7 plus 6 is my total population. And like I said, I'm choosing 4 out of the 13. Now, this is very important, people. If you cannot answer this question, this bottom part, how many do I pick out of the finite population, then it cannot be a hypergeometric distribution. So if you can't answer that, I'm picking 4 out of 13, then this doesn't work at all. Well, that formula doesn't work. Now we're saying, find the probability that this team has only 1 boy. So we go and we say, okay, it's the probability that R is equal to 1. Because I'm now saying picking a boy in this case is like the successful outcome. That's the successful outcome. That's what I want. So I'm then going to say at the bottom here, and this is the part where you say, I'm picking 4 out of a finite population of 13. And please remember, this is combination. We've spoken about that. That literally reads 13 combination 4. But, and now this part I need to split up. So the 13 in the population is split up into those that is successful, so the 6 boys, because I picked boys as being the successful outcome, and then the 7 that is not successful. So that's the 6 plus the 7 gives me the 13. And now the 4 that I pick, I need to split it into what I want over here, meaning I want 1 out of the 6 boys, which means I then want for the rest of my team 3 out of the 7 girls. So that 1 plus 3 is equal to 4. And this is then the probability of picking 1 boy in that team. So let's take a look. I go 6 combination 1 times 7 combination 3 over 13 combination 4. And that is going to give me a probability, rounded off to 4 decimal places, remember, of 0.2937. That is the probability in this team of 4 of picking one boy. Okay. Now, I can also do something like this one, where it says, what is the probability that I pick more boys than I pick girls in this team? So if you think about it, there are 4 I can pick. So if I want to pick more boys than girls, it means I need to pick 3 boys and 1 girl. I can't pick 2 because that's equal. Okay. Now, I don't like this question because the question isn't very clear, meaning I can also pick 4 boys and no girls, which technically speaking, this will also work, because if there's 4 boys and no girls, that means there is more boys than girls, because there are 4 more boys than girls, of which there are 0. So that is why I'm going to assume in this particular instance, it means I can pick a team of 3 boys and 1 girl, or, and this is the word, or I can pick a team of 4 boys and 0 girls. So I'm going to write that down. So it's the probability that I picked 3 boys, or plus the probability that I picked 4 boys. So that means I now just have to use this formula that I've just used. I have to use it twice. 1 for picking 3, or plus 1 for picking 4. So remember, please, the formula, very important at the bottom. It has to do with what you are doing. You are picking 4 out of 13. You're picking 4 out of 13. Here, you want 3 out of the 6 boys, which means you want 1, because remember 3 plus 1 is 4, out of the 7 girls. And check that 6 plus 7 is always equal to 13 here. There, you want to pick 4 out of the 6 boys, and you want to pick 0 out of the 7 girls. So again, 4 plus 0 is 4, 6 plus 7 is 13. So I can type that again into my calculator to work out the probability of having more boys than girls. So that's 6 combination 3 times 7 combination 1 divided by 13 combination 4 plus 6 combination 4 times 7 combination 0 over 13 combination 1. Sorry, 4, not 1. And that is then going to give me 0.2168. And that's the probability of having either 3 boys and 1 girl, or having 4 boys and 0 girls. That's your probability. Okay. Right, so that is then pretty much your hypergeometric probability mass function. And we don't really calculate the other stuff that we calculated last week. Meaning, remember last week when we spoke about just the general probability mass function, I showed you the formula for calculating the expected value, mu, or the mean. And I also showed you the formula for calculating the variance, which you can use to calculate the standard deviation. And for the binomial distribution, or the binomial probability function, I showed you the formulas to do the same, the expected value and the variance. But the hypergeometric one, we don't really have calculations there for calculating expected value and calculating the variance. So don't worry about expected value and variance over here. You do have to worry about it in your probability mass functions, your general ones, the algebraic ones that I spoke about last week, and the binomial ones. Okay, so that's pretty much your probability mass functions. Now we need to move on to the probability density functions. So your probability density functions is very different from the probability mass functions. Very, 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 very important to note this. Now, the biggest difference that you have over here is the following. In the probability mass function, you use an input like 3. You say, I want to know the probability of getting 3 successful outcomes. So your input is just 3. You chuck it into the formula or into the function, and your output is equal to the probability. Here it's different. Here you're going to get a function, and that function, beg your pardon, generally it's an algebraic function. So fx can be, in this case, for instance, a straight line. It could be a parabola, so quadratic. It can be exponential. That fx can be any of the algebraic graphs you've seen up to now. But please note, the probability in this case is not equal to the function. The probability of x lying between two values, and I'll talk about that just now, is the integral of fx. So in other words, visually what that means means this. If you have a probability density function, then this y value does not represent your probability. That's not your probability. But if you want to know what's the probability, beg your pardon, that x lies between a and b, so there's a and there's b, then your probability is the area under the curve between that a and that b value. Because that's what it's saying. It's saying a probability density function, the probability is the integral, so the area underneath the curve. Very, very important. This right there, the area is the probability. Not the y value. And that's what makes the biggest difference between a probability mass function and a probability density function. Then the other thing you have to realize is a probability mass function has what we call a discrete random variable. So discrete random variable is that whole thing like with the boys and the girls. What's the probability of having one boy? Or what's the probability of having 2 boys? Or what's the probability of having 3 boys? Here, it doesn't work like that. Here they would say something like, for instance, this function represents people's income. So it represents people's income. So what is the probability that an income lies between? And it's always going to be between 2 values because this is going to be a continuous random variable. So continuous random variable means it's not just going to be discrete values like 1 or 2 or 3. It's going to be what is the probability that somebody's income lies between 10,000 and 30,000. And that's why you then have to look at everything in between as well. Everything between 10,000 and 13,000. And to work that out, you work out the area underneath the curve between those 2 values. So we'll see just now in the example, it's continuous. So it's always going to be between 2 values. And very important, the area is the probability. So it's not fx that's equal to the probability, it's the area. That's what that integral means. That's equal to the probability. Okay. Now, these probability density functions can be defined mostly in 2 ways. The first one, by a formula or an algebraic expression. So this is just a straight line formula. But you have to understand, fx is not the probability. So if you just go and you substitute something into x and you work it out, then you're getting fx, which means you're not getting the probability. You have to get the area underneath the curve of fx to get the probability. Now, obviously, this algebraic function can be represented graphically. So if I represent it graphically, that's just a straight line. And the straight line will kind of run from there to there. And the reason it will only run from there to there is because we normally have a domain of values. So we have here all the possible values that work. And there's a good reason for it. So it'll start like here at 0, and it will end there at 1. And the reason because of that is the following. if you look at the area underneath that curve from 0 to 1, that must be equal to 1. Because just like with your probability mass functions, where we said the sum of all your probabilities must add up to 1, in this case, the total area underneath the curve must add up to 1. So that is why it's very, very possible that you will have a curve that will start somewhere and stop somewhere. Because if I draw it further, then the area underneath the curve is not going to add up to 1. Whereas the area underneath this curve has to add up to 1. Okay, very, very important. That's why there's always a restriction here, saying that this is my probability density function, but only from 0 to 1. Because anywhere else, there's no more probability, which would just be a flat line. If you think about it like this, anywhere else, there's just a flat line. Anywhere else, there's just a flat line, which means there's no area there. So the probability lies there. That's where it lies. Okay. Everybody happy with this so far? Kind of get it, because we're going to do some examples just now, so hopefully that'll clear it up a little bit more. So this is in your textbook. It's example 1 on page 197, and they give you the following. They say fx, so this is a probability density function. So they've defined it saying this is a probability density function. And fx is equal to kx, but only from 0 to 2, and then 0 otherwise. Now they ask you to find the value of k. And just like with the probability mass functions from last week, we're going to use that idea that the total probability is always equal to 1. But that means, and careful, that the total probability will run from 0 to 2, and that's going to be the area underneath the curve. So I know the integral from 0 to 2 of that fx, so kx. Don't forget the dx, otherwise the notation is wrong. So that total area underneath the curve is equal to 1. Okay, so I can now work out the k value quite easily because I have this lovely integral button on my calculator that I can use as long as it's a definite integral. And this is a definite integral. So generally, they don't say you have to show all your calculations. Generally, they just give you that, and you can very easily then do this. Please remember k is a constant value, and any constant multiple in an integral I can take out to the front. So I can say k times the integral from 0 to 2 of x dx is equal to 1. So to calculate k, I can then just go and say it's 1 divided by this. So 1 divided by that integral from 0 to 2 of x. And that's going to give me a half. So k is equal to a half. Simple as that. Very, very simple and straightforward. Because like I said, the total area underneath that curve from 0 to 2 is equal to 1. If they want to call this a probability density function, otherwise it's not a probability density function. So now we've got k, so we know k is equal to half. Now they want you to find the probability that x lies between 1 and 2. So for x lying between 1 and 2, again, the probability is the area underneath the curve. So the probability that x lies between 1 and 2 is going to be the integral from 1 to 2 of that kx dx, but please remember we've now calculated k as being a half. So I'm just going to put it in there. So that's a half x dx. And again, people, because this is a definite integral, I can very easily just type it into my calculator and say integral of a half x from 1 to 2. And that's going to be equal to 3 over 4 or 0.75. So the probability in this particular probability density function that x is a value between 1 and 2 is 0.75. By the way, sometimes what they do is they show included. So they say x greater than or equal to 1 and less than or equal to 2. And sometimes they just show the greater than, less than. That really doesn't make a difference. It really, really doesn't, because the understanding is pretty much this, if you think about it. If I look at this example, If I look at the area underneath this curve, and I don't include 1, so I don't say equal to 1, I say just before 1, so I go 0,9999999, then that last little area is so small, so tiny, you can actually ignore it. It's negligible. You really, really don't have to take that into account. So it really doesn't matter if this is included or excluded with these probability density functions. You can just calculate it like that from 1 to 2. Okay. Then, next, exercise 2 on page 198. So it's also in your textbooks. This one then says f(x) is equal to 0,2 minus 0,02x. So that's again just a straight line. And x is a value between 0 and 10 and 0 otherwise. Determine the probability that x is less than or equal to 4. Now, please be careful here. I know they only give you the 4, but you need to work with this as well. Meaning, if they don't give you a bottom limit here, they only give you an upper limit, then the bottom limit is automatically 0 over there. It's automatically 0. Or if they give you something like, what's the probability that x is greater than 3? So greater than 3 means they give you the bottom limit, you use their bottom limit, but if there's no top limit, you automatically have to use their top limit. So this is then going to be equal to, and again, the probability here is the integral. It's the area underneath the curve. And here specifically, it will go from 0 to 4. Of that particular function, so 0,2 minus 0,02x dx. And then you can just type that into your calculator because it's a definite integral. So there we're going to go 0.2 minus 0.02x from 0 to 4. And that'll give you 0,64. So that's the probability. Then this one as well, the probability in this probability density function, again, is the integral, the area underneath the curve, from 2 to 6 of that one that they defined. And I can again just type it into my calculator. So this is going to be equal to 0,48. And that's if they give you the formula. It's actually very, very straightforward to use. Okay, so we're going to do a couple of examples from past exam papers. And this is in your notes, by the way. So those notes that you either printed yourself or I gave to you, these ones, let me just bring this up. These ones. So this is specifically on page 3. It's on page 3. And it's quite interesting. You'll see here in the IB AP Maths paper 2008, question 4.4, they said a probability density function for x, the delay in hours for a flight from Cape Town, is given by this formula. And you might actually recognize this formula because this is the example we just did. They didn't put a context to it in the textbook, but over here, this is exactly the same thing. It's the same straight line, it's the same values over there, everything there. And this one, find the probability that the delay will be between 2 and 6 hours. We actually just did that. So in the textbook, we just did that one where we said the probability from 2 to 6 is 0,48. So in this case, the probability that the delay will be between 2 and 6 hours is 0,48 because it's exactly the same function. What I do want to look at, I want to look at this one, find the median of the distribution. That's the new one, the one we haven't looked at yet. Okay, so let me just rewrite this quickly. Sorry. Right. Now, I find sometimes that if you draw like a little picture of it, it actually makes a lot more sense. So this is a straight line. It doesn't have to be perfect or accurate or anything like that, but this is a straight line with a negative gradient. So it kind of goes like this. There. And I know that it runs from 0 over here to about there, which is 10. And I know that the total area underneath the curve is equal to 1. So I know this total area is equal to 1. Now they want me to calculate the median. So the median, if you think about it, is that value for which the area less than that is going to be exactly equal to the area greater than that. Because the median, if you think about it, is the middlemost value. But it's not the middlemost value in terms of between 0 and 10. It's the middlemost value in terms of where the items lie. And logically speaking, that means it's where the area there is 0,5 and the area there is 0,5, because remember the total area is 0,1. So that right there, this is my median. And it makes sense to put this median slightly less here, because obviously that's going to be a slightly bigger area because the length is more than it is over here. So this one needs like more of a width than this one does for that to be a 50-50 area. So in order to do that, to get that median, I will then go and say, okay, but that means I need the value here for which the area underneath the curve is 0,5. So it's the integral, which is the area underneath the curve, from 0 to the median of that function. That, instead of being equal to 1, it must be equal to a half. By the way, you could have set it up differently. You could have said from m to 10, the area must be equal to a half. So you can go from 0 to m, or you can go from m to 10, but it's actually easier to do it from 0 to m, and I'll explain that to you just now, because you can't type this into your calculator because you don't know what this value is. Yeah, sure, you can use inspection and keep on typing in different m values until you get 50%, but that's going to take you forever and a day. It's actually going to be easier just to say to yourself, I have to integrate this. I have to work out the area underneath the curve. So I need those block brackets. Integrating that is 0,2x minus. Integrating that is going to be minus 0,02x squared divided by 2. Because remember, we make the exponent 1 more, and then we divide by the next new exponent. So because I'm dividing by 2, it's going to be 0,01x squared. That's it. And I'm saying I need to work out that area from 0 to m, and that needs to be equal to 0,5. So now I will substitute m in there into the place of x, and then I will subtract, and I will substitute 0 in there. And that's why it's actually easier to put 0 in there, because the moment I put 0 in there, it just becomes 0. So I'm saying it means this, 0,2 m minus 0,01 m squared minus, and then that whole thing is just 0, so I actually don't even have to write this, is equal to 0,5. And then you can actually now use your calculator, because this is a quadratic equation, so you can use your calculator to solve the quadratic equation. Let me just put it in standard form. So that's going to be 0,01 m squared minus 0,2 m plus 0,5. Okay, and very careful, please remember, the m value we're looking for must lie between 0 and 10. The m value we're looking for obviously can't be less than 0 or greater than 10. So I'll change it to equation mode, which is my quadratic equation over there, and I'll say my a value is 0,01, my b value is minus 0,2, and my c value is 0,5. Now this is 17,07, way too big. That can't possibly be my median. So I press the equal button again. This one is 2,9289. So that one is then my median. And this is how I calculate the median of a probability density function. The median of a probability density function. I did give in the notes, I gave you a summary about this as well. So if you just page down in the notes to the next page, you'll see there it says how to determine the median of a probability distribution or probability density function if the variable is a continuous variable. So it says there, just solve for m from whatever your a value, which is the start value, to that median value, and your area underneath the curve is then equal to 0.5. Because remember, m is the median value of the probability distribution. It's the middlemost value. It's that value that divides it into a bottom half and a top half. So 50-50, 0.5, 0.5. Okay, let's look at the next example. Now this is from the IB 2011. So this one then says, a random variable has a probability density function. So again, they define it as a probability density function. By the way, if you get confused between a probability mass function and a probability density function, the mass function is never set up to say fx is equal to. The mass function, remember, is always set up to read p x equal to x. That's how you know it's a probability mass function. Whereas a probability density function is set up as fx, but what they don't give you, what you have to know, this has got to be common knowledge with you, is that fx is not the probability, because clearly it says it's fx. It's not the probability, it's just fx. The probability is going to be the area underneath the curve. So the probability is going to be the integral. Very important. Okay, so let's just write this formula down. And you'll see this one is cubic, which is quite possible. It can take on any of the algebraic equations. And then 0 elsewhere. Right, so the first one they ask us, they say, show that k is equal to 4 over 27. So this is very, very, very similar to the one we did from the textbook. Right, let me show you. So I know that the area underneath the curve of that function from 0 to 3 has got to be equal to 1, because they've defined this as a probability density function. So I know that the area underneath the curve has got to be equal to 1. So the first question that I've got here, let me just see what the numbering is of this question, it's 6.1. Right, so 6.1. I can then set it up saying the integral, or the area underneath the curve, from 0 to 3 of that must be equal to 1. So you have to set it up like that. Then, because this k is a common multiple, I can take it out. Remember, you're always allowed to do that with integrals. And then I can actually calculate this and say 1 divided by that is equal to k. So let's do that. 1 divided by that integral of 3x squared minus x cubed from 0 to 3 is equal to 4 over 27. So that means k is then equal to 4 over 27. Okay, not too bad. Now the next question then says, the mode of a continuous data set is the value of the random variable where it is the most dense. In other words, where does the density function reach a maximum value? So what you're looking at pretty much is you're looking at the following, and it helps again to just draw it. Just do it like this. So again, this is not going to be accurate by any stretch of the imagination, but this cubic graph has got a negative a value. So because it's got a negative a value, it's supposed to look something like this. Okay, but we are only looking at it between 0 and 3. So we're ignoring everything else. We're just looking at it between 0 and 3. So clearly I don't know really where this is. I would probably assume it might be somewhere over here. So I might say this is 0. I might say this is around about 3. And we are looking to find the mode of that little piece right there. So the mode of that little piece is where I have the most values. So it literally means the maximum turning point of this graph. So this right there is the mode. And this is why suddenly now, instead of working out the area underneath the curve, I'm going to have to work out the turning point. And it's only with a mode that I have to work out the turning point, because whatever this value is, that right there, this is my mode. I should rather say this is my mode. This isn't my mode. This is where the mode is located. So therefore, I'm now going to take this function, but obviously I now know that k is equal to 4 over 27. So I'm going to say 4 over 27 times 3x squared minus x cubed. And I'm going to find the derivative of that. And I'm going to set that equal to 0, because that will give me the x value of the turning point. So the derivative of that, if you think about it, we can probably distribute that 4 over 27 just to make it slightly easier. So let's just go and say 4 over 27 times 3 gives me 4 over 9. So I'm going to have 4 over 9x squared, which means if I multiply the 2 by the 4 over 9, it's going to be 8 over 9x minus 10, and then again that's going to be 4 over 27, so that's going to be 3 times 4 over 27, which is again going to be 4 over 9. And then that's going to be x squared, and this is going to be equal to 0. Right, so I can then take out 4 over 9x as a common factor, and I can say this is then going to be 2x minus x, 2 minus x, sorry, is equal to 0. So that means x can be equal to 0, or x is equal to 2. But if you look at the shape of the graph, you'll realize there it's 0. There, I don't have a maximum. There it's 0. I have a minimum. By the way, if you didn't realize that the graph is going to look like this, you can always sub that 0 in to check whether it gives you a maximum or a minimum, or you can just use the shape of the graph. The shape of the graph pretty much tells you the first x value here is going to be a minimum. The second x value there is going to be the maximum. So that means the mode is equal to 2. So these were some odd questions that was asked on these probability density functions, which aren't common questions. I think this question, the mode question, they've only ever asked it once. The median question they've asked quite a few times. So that one you definitely need to be aware of. Okay. And I also gave you in the notes here how to determine the mode of a probability distribution if the variable is a continuous variable. And I just said there, solve the first derivative equal to 0. Now let's look at the next one, and I actually want to give you some time to try this one on your own. It says, question 4, it is given that the probability density function of the distance, x, in meters that a missile falls from the intended target is that. So that's your probability density function, and it's only applicable from 0 to 3. So first question, show that k is equal to minus 2 over 9. That's pretty easy. We've done quite a few of these examples, so I want you to try it. Then calculate the probability that the missile will fall within 1 meter of the intended target. So obviously, because x is the distance from the target, if you want it to fall within 1 meter, it means it can fall from 0 to 1 meter. So it's the probability from 0 to 1. And then right there, calculate the median distance that a missile falls from the target. So please try this one. I'm not going to give you a lot of time. I'll give you about 5 minutes to at least try and see if you can get to 4.2, 4.3, and then we can discuss it. But please try it on your own. And if you have a question, please ask me. If you have fallen to sleep, please wake up. You have something you need to do. Right, let's take a look at this. Okay, let me just copy down the function. Sorry. And this is from the 2013 IB paper. Okay. Okay, so they want you to calculate the value of k or show that the value, I think, is minus 2 over 9. We'll figure it out anyway. Because when you calculate k, you just say the total area underneath the curve from 0 to 3 of that function. And don't forget the dx over there, what's your notation, has to be equal to 1 or else it's not a probability density function. So I can take k out as a common factor, and I can even go it's 1 divided by what's left. So it's that 0 to 3 of x minus 3 dx. So we're going to say it's 1 divided by x minus 3 from 0 to 3. And that's going to be minus 2 over 9. Pretty easy. Okay. Then the next one, 4.2, is calculate the probability the missile will fall within 1 meter of the intended target. So within 1 meter of the intended target, then just means the probability that it will fall between 0 and 1 meters. So that is the probability that X will lie between 0 and 1. And by the way, like I said, you can put that equal to or not equal to, that really doesn't matter. This is going to be equal to the integral from 0 to 1 of that. And you can even put the -2/9 outside if you really want to, because it's a constant, but it's up to you. If it's inside, it really doesn't matter. Of that x minus 3 dx. And you can just type it into your calculator. So I already have the -2/9 there. So I'm going to say it's -2/9 times the integral from x minus 3 from 0 to 1. And that's going to be equal to 5/9, or 0,5556. Who got this one right? Anyone? Who wants to brag? Is anybody still there, by the way?
Yes, ma'am.
Oh, thank goodness. I was very worried that I've been teaching to myself for like the last 20 minutes. Okay. Was there some of you who got it right? Who got this right? Did you get this point at least?
Yes, ma'am.
Excellent. I'm very happy to hear that. Okay. Then 4.3 was the whole one, calculate the median. So the median, like I've explained to you guys, is you say, and you can again put that -2,9 outside. It's just a little bit easier to do it. So you can put the -2,9 over there. From 0 to the median value of that x minus 3 dx is going to be equal to 0,5. By the way, if you did leave that -2,9 inside there, that's 100% fine. But this actually makes it easier to do, taking that -2,9 out. Because I can then actually go and divide the 0,5 by the -0,29. So I can do this. And then I can say this is -9/4. Okay, and then this one, I have to integrate from 0 to m. So this is going to be x squared over 2 minus 3x. And then I can just substitute the m and the 0 in there. And remember, we substitute the m into x, and then we subtract, and then I substitute the 0. But the nice thing about the 0 is I can just say 0. And then I can say that plus 9/4 is equal to 0. And I can just put it into my calculator again. So A is 1/2, B is -3, and C is 9/4. Which means I have the first value, which is 5,1213. Now that can't work, obviously, because I can only have values between 0 and 3. So I press the equal button again, and then I get 0,8787. So that's going to be my median value. Who actually got this one right? Is there anybody who got this one right, or did I stop you too early before you could get there? No comment. Okay. I'm hoping some of you at least got it right. Okay. So I think you'll see that once you've done a few of these ones, it's really not that complicated. It really, really isn't. The only thing you have to remember here is you have to remember there's a very, very distinct difference between a probability mass function and a probability density function. So just to quickly remind you, you can even see it in the notation. So the notation clearly says, if it says this, if it goes the probability that x is equal to x equals blah, 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 that can only be a probability mass function because it tells you the probability is the function. So this is probability mass function. And all you have to do is you just have to do a substitution. So you just, if they go, what's the probability that x is equal to 1? You just substitute 1 into whatever this formula is. What's the probability that x is equal to 5? You substitute 5 in there. By the way, they can also do something like this, where they say the probability that x is less than 5. They can do that. Because remember with this one, they would have something like x is an element of, because remember here they always say for a probability mass function, they go and they say x is an element of 1, 2, 3, 4, and it might go 5, 6. I'm running out of space there a little bit, but you get the idea. So then the probability of x being less than 5, you're not going to substitute every single known value known to man in there. You're just going to substitute 1, 2, 3, and 4, because those are the values less than 5 in my domain. Okay, and they're discrete values. That's why they list them like that. You go 1, or, so plus, 2, or, so plus. So you'll substitute 1 into the formula, plus. You'll substitute 2 into the formula, plus. So they can do this, but you're still working with discrete values. This is my probability mass functions, the ones we did last week. Whereas for my probability density functions, they don't define it like that at all. They define it as fx. They go fx is equal to, and they give you like a formula. But here, you can't just substitute in to find the probability. Here you have to set up an integral because you have to calculate the area underneath the curve in order to find the probability. Okay, and also here they will define it as a continuous variable, so they'd say something like this lies between 0 and 4. So it's all the values between 0 and 4, so that is also different. So please don't get confused between the two. And they have to tell you what it is as well. So read that little letter before you start with the sum that tells you it's a mass function, which means just a substitution, or it's a probability density function, which means setting up an integral, working out the area underneath the curve. Okay, so that's pretty much probability density functions. Thank you very much for joining me. Let me just stop the recording. There should be like a shortcut button for this, because every single time it takes me forever just to find the stop recording button.